Welcome to College Algebra, Chapter 2, Section 3, where we'll be talking about linear functions and slope. I'm going to be working through some slides that were adapted from Blitzer's College Algebra 5th edition. And let's get to it. Linear functions and slope. So sometimes you're going to see, in particular in a statistics class, you'll see data presented on a graph as a series of points, and that's called a scatter plot. And if there's a line that's drawn through what you could maybe call the middle of those points, that's called a regression line. And depending on how closely all of those points on the scatter plot, depending on how close those points are to the line, on average, there's a value that's assigned to describe that closeness. And again, that's the kind of a number that you would learn how to create in a statistics class. And we're not going to be doing that here. But just realize that that's a line that you could run into, and you'll want to know the slope of that because generally speaking, it's describing the trend of the data. The slope of a line can be said to measure the steepness of it. I live in Florida. I grew up in Florida, so I always think of Florida when I'm looking at a horizontal line because Florida is very flat and doesn't have really a slope. So a horizontal line we'll discover has a slope of 0. The way that you go about calculating the slope of a line, at least between two particular points, is to find the difference in the y values of those 2 points and divide that by the difference in the x coordinates of those 2 points. And we often describe that as rise over run, change in y divided by change in x. And if we happen to be looking at a vertical line, the x coordinates of those 2 points are going to be the same, which means this subtraction problem down here would result in a 0, and you would have division by 0. And when you divide by 0, the result of that is often described as being undefined. So we want to avoid using that process if it turns out that the x coordinates are the same. In other words, we'll use this technique where the difference between the x values does not equal 0. And here's a little illustration of it. I won't spend too much time there because my guess is you're familiar with rise over run. We've got these 4 general categories. If we calculate the slope, and as the graph goes from left to right while our x values are increasing, if our y values are also increasing, we say that the slope is positive. If, as we go from left to right, we're going, so to speak, downhill, we say that that line has a negative slope, and it will. We can calculate it. There's Florida with its slope of 0, and here's our undefined slope. Vertical lines have an undefined slope. The relationship between this equation, which is called point-slope form, and this equation, where's my eraser? If I put an m in front of this equation to describe slope, if we were to multiply both sides of that, if we multiplied both sides of that equation by x2 minus x1, then that would disappear from here. It would appear up here multiplied by the m, and this equation really is this equation. So the relationship between point-slope form for a line and the calculation of slope, those 2 things are obviously very related now. The point-slope form equation for a line is most frequently used when the data that's available to you can help you find the slope, and when the data given to you contains a particular point, x1, y1, and we're seeing those values here. And don't worry, we're going to look at an example of this if you need a refresher on point-slope form. There's another form of the equation of a line that you are also maybe very familiar with. It's called Slope-Intercept Form, and it is y equals mx plus b. Slope-intercept form is just a little bit vague. The slope is definitely represented by this m value, which you can calculate by doing rise over run between 2 points. But this b value isn't just any intercept, it's the y-intercept, and that's illustrated and written for us right here. Y-intercept is b. And there is the actual y-intercept, 0, b. We're going to do some graphing using slope-intercept form, and when you're graphing an equation online, like in My Math Lab or Connect Math or wherever, sometimes using slope-intercept form is very helpful because you can start at your y-intercept and then either count up and over or down and over using your rise and your run in order to find the location of another point that you can click on, and then you'll snap your line to it and you'll have the correct graph. You could also use that if you were graphing by hand. In this case, we're going to, in example number 7, there it is, we're going to use these given conditions to write an equation for a line in point-slope form, and then we'll convert it over to slope-intercept form. If I didn't have these somewhat elaborate instructions, and I just said, write me the equation for a line that passes through these 2 points, how would you know which version of the equation of a line to start with? Well, you could ask yourself, should I use point-slope form? And then you look at the available data, and you say, well, I've got a point. In fact, I've got 2, but I don't have the slope. But you know how to calculate the slope. So the data available will allow you to quickly calculate the slope. Then we'll mix that in or utilize one of these 2 given points, and we'll have an initial equation for our line. So let's do that. Let's calculate m first. That's y2 minus y1 over x2 minus x1. And just in case you're the kind of person who might get distracted and not remember which one is 1 and which one is 2, I like to go in and label them. I'll call this x1 and y1, x2 and y2, and that way I make sure to plug them into the right place in this formula. So I have -1 minus my y1 value, which is -4, and notice I'm putting that -4 in parentheses because I have to address the double negative there. x2 is a +1 minus x1, which is a -2. Again, I'm using those parentheses to help make sure I account for the double negative. In the numerator, I've got -1 essentially +4 because of the double negative. -1 plus 4 is 3. And in the denominator, I've got 1 plus 2, which also makes 3, and we end up with a slope of 1. So I put a circle around that to make sure it doesn't wander off. And now, let's frame things up using point-slope form. Point-slope form says y minus y1 equals m times the quantity x minus x1. We know we've got 1, 2, 3, 4, 5 unknowns in this. All we need is 3 of them. Let me show you. I'm going to keep the y and the minus sign, and then I'm going to replace y1 with what we've already designated as y1. So that's going to be the -4, which I'll put in parentheses again, equals, we calculated m. You don't really need to write the 1, but I'm going to write it initially, times the quantity x minus our x1 value we decided was the x-coordinate of that first point, which was -2. And this is the equation of our line. Let's clean it up a little bit. let's write it as, and if you want to label this, this is point slope form, and then we substituted in those values. And I would write the left side of this as y plus 4 equals, maybe keep the 1, maybe don't. So this maybe is how your professor, instructor, teacher would want you to write the equation in point slope form. Maybe they would want to see the 1 in front of it so that they know that you did take the time to calculate the slope. So that's our answer in point slope form. Now how do we write this in slope-intercept form? This one's pretty easy, in particular because we have an m value of 1, so we don't have to worry about distributing multiplication by 1. That's pretty uneventful. All we have to do is get the y value isolated on the left-hand side. We're going to do that by subtracting 4 from both sides. So I'll put a little note here that I'm subtracting 4 from both sides, and we get y equals x minus 2. And this is our final answer in slope-intercept form. From slope-intercept form, it's very easy to do our graphing. And I don't think this question asked us to graph it. It didn't, but let's graph it anyway. Is there an available graph that we could use? Not nearby. Okay, so let's just draw ourselves a quick graph. And maybe we'll go 3 points in either direction. And then the first thing I'm going to do is plot my y-intercept. The y-intercept is -2. So let's plot that point, 0, -2. And then I'm going to use my slope, which it's kind of nice. Up here we saw that the slope was equal to 3/3, which turned out to be 1. Realize that that's also equal to 1/1, or 2/2, or -3/3. All of those fractions are equal to 1. -1/-1. All of those fractions equal 1. And I mention that because from this point, from this y-intercept, we could rise 1 and run 1 in order to arrive at another point on our line. We could have risen 3, 1, 2, 3, and then run 1, 2, 3 in order to arrive at another point. We could have gone down 1 in the y direction and then left 1 in the x direction, so that's down 1, back 1, and plotted another point there. And you'll see that even in my hand-drawn version of this line, all of those points are collinear. They're all on the same line. Do I need to use -1/-1 sometimes? It depends. But every once in a while you get into a bit of a jam, and it's helpful to go down and left instead of up and right. Okay, so that's point slope form, slope-intercept form, and just a quick bit of graphing. Again, we're seeing that a horizontal line has a slope of 0, but generally speaking, the equation for a horizontal line is written as y equals some number. And look, this line has a y-intercept of b. And in generality, this is a little bit awkward of a conversation. Let's pretend that our b value is a 3. So we could put some marks over here on this so that we can see clearly that our horizontal line passes through the y-axis where y equals 3. That means that this point is now 0, 3. And let me ask you this question. what's the y-coordinate of this point? What's the y-coordinate of this point? Or this point, or this point, or this point, or this point, or any of the other points on that line? They all have a y-coordinate of 3. So all of a sudden, the equation of this line being y equals 3 maybe makes a little bit more sense. A good way to describe that line. A vertical line, similar, but with a little bit of difference, is described using an equation x equals some number. And we could go through all of those same motions describing why x equals 4, for example. 1, 2, 3, 4. This point has an x-coordinate of 4, this point has an x-coordinate of 4, this point down here has an x-coordinate of 4. So it makes sense why x equals a number is the best way to describe mathematically a vertical line. Why would it be that a vertical line is not a linear function? It has an equation. Doesn't that mean that it's a linear function? Don't forget from a previous section that we said a function is a relation that does not contain any repeated x values. Hello. Every one of the points on this line has the same x value. This is the most egregious repeating of the use of an x value that exists. This one is super fail, not a function. It fails the vertical line test infinitely many times. And then there's this wonderfully well-named version of the equation of a line. It's called general form. You'll see this every once in a while. It's got everything balanced over to the left-hand side. A, B, and C are real numbers. The right-hand side is a 0. Is there a benefit to writing an equation of a line using this format? Not that I can think of off the top of my head. Other than the fact that it's sort of like a reset, it's sort of like a starting point. And then we can terrorize you with questions like this one, having given you the equation of the line in general form. So if we wanted to find the slope and the y-intercept of the line that's described by this equation, how would we go about doing that? Well, I'll tell you, it'd be a lot easier to find the slope and the y-intercept if that equation were written in Slope-Intercept Form. So my recommendation is that you manipulate this equation until it is in Slope-Intercept Form. Let's do that. Slope-Intercept Form is y equals mx plus b form, which means we need the y to be all alone on the, in this case, the left-hand side of the equation. But the first thing that I'm going to do, which you might not have thought to do, is I'm going to make all of my numbers a little bit smaller. Every one of these coefficients, the 4, the 6, and the constant value of 12, they're all divisible by 2. So I think I'm going to scale this thing down by dividing the entire equation by 2. And the result of that will be 2x plus 3y plus 6 equals 0, because 0 divided by 2 is still 0. And then let's start moving everything except for the y term over to the other side of the equation. Let's subtract 2x from both sides, and let's subtract 6 from both sides. That leaves the 3y right where it was, and it equals negative 2x minus 6. Because 0 minus 2x equals negative 2x, and 0 minus 6 equals negative 6. Then we need to remove the 3 from the y. The 3 is connected to the y by multiplication, so we will detach it using the opposite of multiplication, which is division. So we'll put a little note here that says we're going to divide our entire equation by 3, and I will write that as y equals negative, let's actually do this. I'm going to write it as 3y, I'm dividing it by 3, and negative 2x, which we're going to divide by 3, and minus 6, which we're going to divide by 3. Normally I don't do all of that writing underneath an equation. It looks a little cluttered, but in this case it's kind of nice because it makes it a little bit easier to see, certainly, that these 3's cancel. The negative 2/3 can't be reduced, but the 6 over 3 can reduce. On the left-hand side, we only have the y remaining. The first term on the right-hand side, the negative 2/3 x, we can't do anything with that, so I'm going to leave it as and you'll notice that I've written the x next to the fraction instead of in the numerator. That's allowed. That x is still considered to be x over 1, which would push the x back up into the numerator where it came from, so those are equivalent. And then minus 6 divided by 3 is 2. Oop, I don't want to put a box around that. I've only put the equation for the line into slope-intercept form so that we could more easily identify the slope and the y-intercept. Our slope is most definitely negative 2/3, and the y-intercept happens at negative 2. And there we go. We've got our answer. It's A. Nice job. Using intercepts in order to graph an equation that's given to us in this general form. We saw some illustrations of it I showed you earlier, but let's just revisit one more time very quickly. Remember, the y-intercept is the point where our graph crosses the y-axis. Do we know the coordinates of this point? I know one of them. I know that the x-coordinate is 0, and I don't know what the y value is. But if I'm on the y-axis, then definitely the x-coordinate is 0. Similarly, this point that's on the x-axis, our x-intercept, has coordinates. I don't know both of them, but for sure the y-coordinate there is 0. I think I'm even going to go and erase this y that's here. Those are the two things that we know about our x and y intercepts. How do I find, then, how do I find this value right here? Well, if I know what my equation is, I know what my x value is, I can take the x, plug it in, and solve for y. Similarly, in order to find this x value, if I have my equation, I can plug in a 0 for y and solve for x. And that's exactly what we're told to do in this blue box right here, and it's what we're going to do in order to find the intercepts of this line. We'll plot those 2 points, we'll grab a straight edge, we'll draw a line through there, and we will have graphed this line. So first, the y-intercept. If it's the y-intercept, we're on the y-axis, and that means we have an x value of 0, so we will let x equal 0. So we have 3 times 0 plus 5y plus 15 equals 0. And then let's solve for y. 5y equals negative 15. I subtracted 15 from both sides, and then I'm going to divide both sides by 5 to get a y value of negative 3. And there's your y-intercept. That wasn't so bad. Let's do that again. To find our x-intercept, we're going to let, this time, our y value equal 0. 3x plus 5 times our new y value of 0 plus the 15, still equal to 0, bringing the whole equation with us. This time we need to solve for x. Still subtracting the 15 over to the right-hand side, so I'll put a little note here about minus 15. This middle term is gone because of multiplication by 0, and we end up with 3x equaling negative 15. Divide both sides by 3, and we get an x value of negative 5. Then we can take those two intercepts and let's go 1, 2, 3, 4, 5 units in the negative x direction, 1, 2, 3 units in the negative y direction, and there's our y-intercept at negative 3, there's our x-intercept at negative 5. Grab your straight edge, pass a line through those 2 points, and you graph your line. If you're graphing this line online, then those are the 2 points that you would need to click on in order to get this answer correct, because you were told to use the intercepts to graph the line. Although the instructions are hiding behind me, there you go. Is it possible that I could click on 2 other points in order to get the exact same line? Absolutely. But if you're using an online software in order to complete a homework assignment and the instructions tell you to use the intercepts in order to graph it, the software may very well be using or looking for you to click on exactly those 2 points. And if you click on anything else, it's going to say that you're wrong even though you've graphed the correct line. So do be careful and make sure you're following the instructions carefully and closely. Here's a little summary of the different formats for the equations of a line, and that would put us into Chapter 2, Section 4, which means we are done with 2.3, which means I get to thank you again for hanging out with me for a little while, and I get to invite you to join me in the next section, 2.4, where we're talking about more on slope. How fun is that going to be? See you there.